In today's lesson, we are going to be looking at power laws continued, and now we're going to be introducing radicals or rational exponents. So this might be something that you looked at last year. If not, we're just going to cover it quickly. But a rational exponent is basically we have a fraction as an exponent. And this is where our square roots and our different roots come into play when we're dealing with exponents. So the rule is when we have a power or a base raised to an exponent, if that's the case, and we have a specific root, that simplifies to basically the exponent on our base and the root as our denominator. So essentially, the a comes to the top, the b comes to the bottom for our fraction, and that is how we convert between radicals and rational exponents. So just for some terminology, this kind of symbol, this kind of the root symbol, that's considered our radical. We also have our root or indice, is what it is, that term for the number that's out front. And then the part that is under the radical, this is called our radicand. So again, terminology might not necessarily be important as long as we understand where the two values are going to become part of our fraction. So the number that's attached to the base is going to go onto the top or our numerator, and then the root or the power out, or the number out front is going to become our denominator. So here, the fifth root, that's how we would pronounce that 5 with the radical, the fifth root of 2 to the power of 9. So this would mean our base would be 2, our numerator would be 9, and our denominator would be 5. So we, instead of writing the fifth root of 2 to the power of 9, we can say 2 to the power of 9 over 5. And we can use that to evaluate if necessary to get our answer. So I'm going to go through this one. And it is helpful to turn it into a fraction exponent, because in some cases, chances are you are going to have an exponent button, but not always are you going to have the option to change this value in front of the radical. So if we evaluate this, we get 3.48. So basically that the fifth root, remember, is similar to the square root. Fifth root just means something times itself 5 times. So 5 times 5 times 5 times 5. Or no, sorry, not 5 times 5. A number multiplied by itself 5 times gives us a value. So something times itself 5 times equals whatever 2 to the power of 9 is. So let's go through and practice writing some of these out in radical form. So we're just going to work on converting between the two. So 2 to the power of 5 over 2. The 2 comes out front. 2 is our base, and then we have a 5 as well. Now in this one, we commonly see the 2 not existing in terms of the indice, because normally our general form of a radical is the square root. That's our lowest form. So similar to how if we don't see an exponent, we assume it's 1. If we don't see a value in front, we assume that it's 2. So we could put the 2, we don't have to. Next, 7 to the power of 10 over 11. So 11 becomes our indice. We have 7, and then to the power of 10 underneath our radical. Same thing applies even if we have variables. We can't really see this too much, but 8 over 3, x to the power of 8 over 3. So 3 goes the number up front for a cubed root. We have x to the power of 8. Here we're just going to go and write these as exponents. So again, just kind of going in the other direction. So our base is 5, 7 is our numerator, 4 is our denominator. 5, 7 over 4. The next one, 100 100th root of 3 to the power of 3. So we're going to have 3. 3 is our numerator divided by 100. And lastly, the 9th root of 7 squared. So 7 squared divided by 9, or 7 to the power of 2 divided by 9. So the next part, let's just go through and use the power laws to simplify each expression, and let's not leave negative exponents in the final answer. So what we're going to do, we're going to go through, even though we have rational exponents, we're going to leave them as such until it's necessary to actually apply some of them. So we have 2a to the power of a half times 5a to the power of 5 halves, or 5 over 2. So again, in a complex base, I can focus on my two numbers. So I can do 2 times 5, which gives me 10. For a, I multiplying power, so I can add the exponent. So 1 half plus 5 halves gives me 6 over 2. I can simplify this. 10 to the power of a to the power, or 10a to the power of 3. So we can simplify our fractions or our rational exponents if it works out to something nicely, or we can always reduce them if necessary as well. So next one, b, 6x to the power of 2/3 times 8x all to the power of 1/3 divided by 4x squared. Again, I'm going to simplify the top and the bottom as much as possible. So I don't really do anything to the 2x or the x or the 6x squared, or x, sorry, not x squared, 6x to the power of 2/3. For the 8x to the power of 1/3, that 1/3 exponent, this applies to both parts. So this becomes 8 to the power of 1/3, x to the power of 1/3. All divided by 4x squared. I can actually simplify the top even further, because 8 to the power of 1/3, or the cubed root of 8, is 2. So this is actually 2x to the power of 1/3. All divided by 4x squared. I can now simplify the top, multiply my two numbers. 6 times 2 is 12. X to the power of 2/3 times x to the power of 1/3. We add, so we just get x to the power of 1 divided by 4x squared. And this simplifies to 3x to the power of -1, or 3 over x. We move our negative down to make it a positive exponent. For c, I have a radical, or I have a root, so I'm going to go through and I'm going to remove that. So x, y cubed all to the power of 1/2 divided by 4xy to the power of -1/2. In this case, normally we would we'd apply the negative exponent through and then worry about it. But I'm actually going to remove the negative first and bring the entire thing up. So I'm going to make that 4xy to the power of +1/2 now. It's a little bit easier when I work through it. So now I'm going to get x power of 1/2, y to the power of 3/2 times 4 to the power of 1/2, or the square root of 4, which is 2, x to the power of 1/2, y to the power of 1/2. 2 is just going to get carried through. X to the power of 1/2 times x to the power of 1/2. We add our exponents, we get x to the power of 1. We get y to the power of 4 over 2, which I can simplify, 2x y squared. So again, different strategies, right, depending on what we have. If we have a negative rational exponent, sometimes it helps if we move it and make it positive rather than trying to take the square root of a number or of a fraction. It's just might be a little bit messy. So it might be easier to move it up. or remove the negative exponent first. You could expand this negative through to each part, similar to what we did in the positive version, and then worry about the negatives at the very end. It's up to you what you feel comfortable with. But the main thing is, do not leave negative exponents in the final answer. Lastly, again, we're going to write each power as a single exponent and then evaluate. We don't want to leave any decimals, so leave them as fractions. So 6 to the power of 0 to the power of -3 times -2 to the power of 5 to the power of 0. So here, 6 to the power of 0 is going to be 1 times -2 to the power of 5, which is a value, to the power of 0, which is 1. So this is 1 to the power of -3. And if I were to flip that, that becomes 1 over 1 to the power of 3, which is 1. So a long ways to go to get an answer of 1. For B, again, I'm going to simplify the top. So -4 is my base. Actually, I have a negative rational exponent on the bottom here. So similar to the last one, I'm going to move that up. So -4 to the power of 5 times -4 to the power of 3/2 times -4 to the power of 1/2 now. Now I'm going to go through, actually let's move this a bit. Now I'm going to go through, it's all the same base, so I'm going to have a base of -4, and I'm going to add up my fractions, or my exponents. So 5 plus 3/2 plus half, so 1.5 plus half is 2, plus 5 is 7. So added up all my exponents, I get 7. And now I can evaluate this. -4 to the power of 7 is 16,384. Now keep in mind, because we have the -4 in brackets, we have to make sure that we include brackets in our calculator when we're doing it. If you were to just do -4 to the power of 7, your calculator would actually read that as -1 times 4 to the power of 7. It's assuming that that negative is not part of the exponent or the power. So that is one reason why, or that is the reason why you want to make sure you include brackets if you see them, to make sure that that negative gets carried through. So this would actually be -16,384 if you didn't include the brackets. So this one is brackets. Green because we want this one, and we'll do red because it's wrong for this question, right? It depends on the question that you have, that you're given. In this case, because we see the brackets, we can assume that the negative is part of the exponent or the base. So technically, looking back, there should be brackets there. So depending on how you look at it, actually, I would say because we move the 4 up, there's actually still a divided by -1 underneath. So let's just move all this down. Oh, we would need the negative, sorry. We would need the negative to go with it in order to simplify because of the same base. So there is just a small typo, so there should be brackets there. But again, the main thing for this one is just working with rational exponents or radicals. It's essentially figuring out what they mean so that we can simplify some of our terms, some of our numbers. We still treat the power laws the same way, adding, subtracting, multiplying. But when we're using them with our numbers, we have to understand that they mean roots, like square roots, cubed roots, and so on, because that will be easier to help us simplify some of our values.